Welcome to Embedded. I'm Alicia White alongside Christopher White. Our guests/co-hosts are Stephen Kraig and Parker Dillmann of Macrofab and hosts of the Macrofab podcast.
Hey, everyone.
Crossover. Sorry.
No, that's cool. So yeah, I'm Parker.
And I'm Stephen. And we're from the Macrofab Engineering Podcast.
And I'm Chris from Embedded.fm podcast. And
I'm Alicia from Embedded.fm podcasts and Logical Elegance and all of the other insane things I get into.
This is going well so far.
Oh, yeah. Okay.
Woohoo! We made it past the intro.
Okay, let's do this. Can you tell us about yourselves? And then we'll share and all of that.
All right. Yeah, I'm Parker Dillmann. I'm an electrical engineer, born and raised in Texas. Started or co-founder of Macrofab. It's been my life for the last 4.5 years now. Do electrical, manufacturing for small OEMs, specializing in doing prototypes and small volume runs, stuff like that. I like Jeeps. I like hunting, camping, fishing, taking things apart. So that's probably what got me into all this.
And I'm Stephen Kraig. I'm also a native Texan for the majority of my life. Not originally, but the majority.
Wait, how can you be partially a native Texan?
Because I have given up my Oklahoma residence.
Oh.
That is no longer. I'm officially a Texan. So I am a general purpose engineer at Macrofab. I have been at Macrofab for 2.5, 3 years, something like
that. Yeah.
So I am a hacker and a hardware engineer. I prefer analog audio electronics. Do a lot of work in that.
Yeah, we're kind of. I kind of do more of the digital stuff, and he does more of the analog stuff. So we complement each other quite well on projects.
You look lovely today, Stephen. All right. Well, I'm Alicia White, a native Californian. Used to live in Southern California. Now I live in Northern California.
Middle California.
Middle. Software by training. Software and general engineer by training. And went to HP when I first got out of school, learned about big companies, and just kept falling in love with ever smaller companies until finally I gave up and founded my own. And now we do embedded software consulting. I do embedded software consulting. Someone took a full-time job.
Went from 1 million people to 2, right?
And now it's at 1. I've been abandoned.
Oh, no.
You've reached full transcendence now.
Yeah, I'm Chris, as we've already mentioned several times. I'm a software engineer as well, and started out also at a big company at Cisco Systems doing networking stuff, and then went to a startup doing more networking stuff, and then a succession of startups after that doing embedded systems things and medical devices, consumer products, all kinds of things. I do not have electrical engineering training of any kind except by osmosis. But I like playing music and the beach.
Yes.
Our beaches are a lot different than yours out there. Ours are a lot more brown and kind of nasty. So I'm excited about this podcast because we kind of have both worlds coming together here. We have the hardware and the software world, and we kind of, I guess we're going to take a peek into the minds of both, right?
Yeah, that was kind of my goal. So we could find out what software and hardware engineers...
Let's find out what's wrong with the other side.
I was going to say want from each other, but we can go with what they hate about each other instead. That works too.
10 things I hate about you.
Okay, so do you want to do that, or do you want to tell us more about your podcast first?
I mean, sure, we can. I mean, so the Macrofab Engineering Podcast actually was created just so we had a blog on our website, macrofab.com. And the problem with blogs is you have to make lots of content, a lot of like over and over regularly, so that you have people coming to your blog a lot. And so I was writing articles at the time. This is before Steven even came on.
I was about to say, because I was writing articles too.
Yeah, but at the very beginning, it was just me writing articles, and I could get like an article out every like 3 months. So it was really slow. And then, because at the time there was like, at the time we had like 6 people here at Macrofab. And so like I was running the assembly line. I was doing like 80 different things. So writing an article was so far back, on the back burner. And so we're like, how can we make more content regularly and make it easy? And that was kind of how the podcast came about. Steven came on board and he's like, yeah, the podcast sounds fun. And we put together 5 in my kitchen and published those, and people seemed to like it. And so we went to a studio and started recording, and now we have our own equipment. Cool. The big thing I try to hammer home with our podcast is it's not an advertisement. I don't like promoting Macrofab on the website, on the podcast. And I like to talk about engineering and our projects and cool things that we see every week. So yeah. Yeah,
and you just kind of get our perspective on either what we're doing or what one of our guests is doing. It's just a bunch of fun, mainly it's hardware stuff, but it kind of covers a lot of other things at the same time, but it's just kind of, a fun thing that we get to do every week.
Yep.
Yeah. And you have guests, but you also talk about news and what's current and all that. We usually avoid news and focus on guests. Do you have any favorite topics you like to hit?
How IoT is. That seems to be a recurring topic.
Yeah, that's there's been plenty of those for sure. And if you look back, there's kind of 2 ways to describe. One way for each one of us, it would be Parker equals Jeep and Steven equals synthesizer.
That too. That's a recurring theme.
Both of those are reoccurring topics for us because we both do a lot of work in those. And it'll be something where if you listen from the beginning, you can hear Parker's Jeep evolve throughout all of the.
It's almost sentient now.
Yeah. And a lot of it is, he's designing some kind of electronics or whatever crazy cruise control crap is going on in there.
Yep.
You need to combine the two. Some sort of Jeep synthesizer.
Oh, that'd be great. But okay, that's one of the biggest problems. I'll say that this is a problem with our podcast is we have gobs of projects that we do, and we talk about that on a regular basis. So thank you, but no thank you for giving us another project to do.
I went through the list of Christopher's project on one show, and it was like 25 things long, and and made him give updates on all of the projects, and it was so ridiculous.
Torture.
Yeah, that is brutal.
Now they're 30, and they're also in the same status they were before.
Yes.
I think if that happened to me, I'd have to go see a therapist.
Well, we haven't finished the project that we talked about on the very first podcast. So
yeah, it's still a box of parts.
It's tough because you do want to talk about interesting stuff, but how do you do interesting stuff every week? I mean, realistically, we have jobs, we do technical things we can't talk about, and so for our hobbies, we're going to do extra electronics, and then we're going to make a podcast about them.
Actually, that's kind of how it works. We usually like alternate which one's project is like the lead at the beginning of the podcast. And so we just alternate. So basically you get 2 weeks to kind of get some progress on a project going.
Yeah, and you're scrambling the night before the podcast to come up with something.
Is this why you started having guests a lot?
Not really. Oh. It's usually guests are just to bring in some outside skill set that we don't really have.
Well, and at the same time, I think as our listener base has grown, so has the desire for guests and people
get bored
asking
of us.
Or, well, yeah, people getting bored. Yeah, they don't want to keep hearing about Jeeps and synthesizers. They want to hear about something else. But no, like we just have more opportunities for guests, so it works out.
Yeah,
and it's fun for the host to talk to guests.
I like that sometimes I can ask somebody I want to ask technical questions of, and I can say, hey, be on the show. And then I can ask them all my personal technical questions and not have to go through like support forums.
Your own personal FAE.
Right.
we actually sort of had that the other week when we had a patent lawyer on and we discussed.
Yeah.
And what, if you listen to that podcast, you get basically your first hour of legal counsel for free in a way, if you really read between the lines.
That's a good one. We had our accountant on once to talk about incorporating businesses and taxes. And it was totally
I need to listen to that one.
Outside the scope of what we usually talk about, but it was fun. And I think a lot of people listened to it.
That's great.
Okay, well, shall we get to the actual how to make stuff? How to make software and hardware engineers work better together. Wow, that really doesn't flow well, does it? So what are the things you hate about us?
What's actually funny is I've actually only worked on 2 projects in my life that had separate software and hardware engineers.
Was Macrofab one of them?
No. It was the previous company I worked with, which was Dynamic Perception, with Church, which is our co-founder here at Macrofab. He was the other founder there at Dynamic Perception, and he was the person who was writing all the code, and I was designing the hardware. So this is going to be a very interesting podcast because I haven't really worked like this before, like with these 2 separate. Like I usually, for my personal projects, I write all my firmware. Now I write it poorly, but I try.
Well, and I think a lot of your projects, they're large, but they're not of the scale that requires a team.
Oh, that's true too. So. Well, no, the pinball controller has a dev team now.
That's true.
Yeah.
Yeah.
So maybe I'll learn something on how to manage that because I have no idea what I'm doing.
Yeah, you'll learn why they hate us, I guess.
Or yeah.
So I've worked on some teams before where I've actually had technically the product line I was working on was owned by me, like my name was on it, but I had a dedicated firmware engineer and a dedicated software engineer who, in all honesty, they were, we all owned the project equally. And so the firmware guy did all the code for my micro that was on my boards, and then the person doing the software, she wrote all the code for the test programs and things like that. So I have a little bit of experience of working hand in hand every day with software guys.
That's funny. I don't work as closely with hardware guys as I used to because I am doing more startup work. And they want breadboards, so then they get prototypes, so they can get venture capital. But I end up buying my boards off of Tindy or Adafruit or SparkFun or AliExpress and just slapping them together and hoping that nothing really goes wrong with that plan. But I used to, sit next to my EE. I used to share an office with my EE, and we would talk every day. It's weird to have more separation than there used to be.
Well, and as the companies get larger, that the separation gets further and further.
Yeah,
you different departments, and then you have meetings that occasionally you'll cross paths, and the occasional schematic review. And usually, there isn't a reciprocal thing of any kind of firmware review by hardware people, but
just a little unfortunate sometimes.
Yeah, and then lots of miscommunication and anger. So I think it's the separation that causes. But no, I think it's the separation that causes problems a lot of times because people will make decisions that they think are best, and they won't even realize that they have some implication. Yeah,
how that affects other aspects of the project.
Well, yeah, and to be honest, in all reality, I see kind of the hardware firmware side. Maybe there's a little bit of distinction when you come to software, but the hardware firmware side, those guys are in bed, all the time. I mean, those guys are linked together almost 24/7 with what they have to do because if any one of those people make a change to a product, it affects everyone else. And so you really have to you have to have real strong communication with your software people and your firmware people, or you will get you will result in anger, I guess, the way you put it.
Well, I don't know. I mean, it depends on your definition of firmware. It's kind of loose.
It's the
we don't want to get started on that.
Drivers.
We've had like full day arguments on where firmware starts and where firmware ends here at Macrofab.
Oh, I don't think there is an answer to that. I mean, when you say firmware, some people will say, oh no, that's the microcode. If you're actually writing in C, that's not real firmware. And other people will say...
Who are those people?
You worked with one of them. Actually, one of them argued with me. One of the people you worked with who wrote microcode. And then there are people who are like, well, if it's not on the web...
That's hardcore gatekeeping.
Yeah.
You must write an object or assembly code to be firmware.
So, I mean, firmware is between hardware and software, and whether the software is on the device or the software is in the cloud, I don't think there's a solid line.
There isn't a solid line in the stuff I do every day.
No.
I mean, people would define what I do in the morning as software, and maybe the afternoon is firmware, and it's all one stack, going kind of morphing from one to the other. So it's it's a tough thing to define.
It wasn't. You were just complaining about you were having arguments with both the hardware engineers and the design team because there was no way.
The industrial design team.
There was no way you could solve both of their problems at the same time.
Right.
So that's firmware for sure.
Yes.
Yeah, we should just argue about this.
Actually, how about this? What makes an embed system embedded?
Oh, God, not again.
No, it's pretty easy. An embedded system is purpose-built for its application. And what that usually means is it's resource constrained. Now, is a phone an embedded system? Well, to the person who has to program the operating system or figure out its sleep states, absolutely, because they are totally resource constrained. To the person who's writing Candy Crush, no, it's a computer. And so you can have different perspectives for the same device, but it's whether or not you are worried about your resources and how you are constrained within them to most efficiently serve the purpose of the device.
So it's a sliding scale in a way. It depends on what you use it for or what part of it you're working on.
Yeah, but of course there are things like Fitbit or microwaves or even cars that you have to say those are definitely embedded because nobody works on them who isn't aware of their resource constraints.
Really?
Sorry. Fitbit now has apps.
That's a really good definition.
Fitbit
I like
runs
that
JavaScript
definition.
apps, so I don't know. But
let me throw a monkey wrench in real quick. What about a Raspberry Pi? Is that an embedded system or not?
Like if you write a Python program that runs on it.
Wait, what if you write a Python program that like spins a servo using some of the pins? Did you just change a computer into an embedded system because you purpose-built it?
I think yes, and I think that's the purpose-built single-use thing. I mean, okay, how about this example? I worked on medical imaging scanners that the main core was a Windows computer. Is that an embedded system? It did one thing.
Yes, definitely.
Yeah, we have a reflow oven that has Windows XP on it. So, I mean, it does one thing, reflow boards.
Yeah. The self-checkouts at Home Depot all run PIC microcontrollers. They are embedded systems. They do one thing.
And so the Raspberry Pi, I go back and forth because that is such a computer. It is such a bigger computer than I had for all of the first 10 computers I had. So how is that not a computer? But then once you put it in a robot and all it's doing is controlling the robot, then how is it a computer anymore? It's a controller.
So I think it can be unuseful to discuss this too much.
Yeah,
because
we jump right to like the meta side of the differences between hardware and software.
But I think, something that interacts with the real world, something that has a single purpose, that's probably a pretty good...
You pass butter.
Yeah. Yeah, you pass butter, exactly.
Okay, but we know what hardware is.
Do we?
Even though hardware isn't as clear-cut as it used to be.
FPGA seems like software to me.
Yeah.
Flat flex PCBs, they're not real hard.
That's true. How do you feel about those? I mean, I see a lot of hardware engineers using them, and I'm like, you can't solder to them, right? And then they come back and they're like, oh, it's totally fine. And then like after 5 of them have burned on their soldering iron, they're all, oh, I wish I'd used a real board.
Oh, we solder flat flex all the time here. It's not a problem.
Yeah, and there's purpose-built soldering irons. They what do they call them? Hot bars. They call them hot bars for purpose-built for flat flex.
They're just really, really wide soldering tips.
On an arbor press, basically. So,
but they're cooler too, aren't they?
Yeah, a little bit. Well, it depends. Because you're still trying to solder lead-free, so you still need the hot
you still got to get hot enough.
So it's actually, sometimes it's even hotter, so it gets a higher impulse with less heat soakage.
Okay. That makes sense. I still don't love flex because I definitely cannot solder on them. And I have watched my hardware engineers flame their flex boards.
They're expensive flex connectors.
And then you're like, I shouldn't laugh. I'll just go to the bathroom.
Oh, so go back to we were talking about Chris was talking about what hardware is. Like, so he brought up the example FPGAs, which is very interesting because what is like VHDL and Verilog code then?
It's a physical definition of metal connections inside of a semiconductor device. So in a sense, it is code.
It's code, but it represents a hardware structure.
Not directly.
It's sort of like a picture, in a way.
I've always thought about it as a logical definition of how things are clocked and what to do when certain clocks happen. And it seems more like C code to me, except all at once.
Yeah, it's a lot like C code. But the thing is, though, it's C code that, well, kind of like, we're talking about Verilog. It's kind of like C code that compiles into a hardware definition of what's going on.
Right, that's what I was meaning by a picture.
Okay.
Like it actually physically changes something in the real world. I guess you could argue that, nah, I'm not going to go there. Now we're getting way too meta. I was about to argue about code changing things in memory, but we won't go down that route.
Yeah, but nobody looks at memory, but you could look at a schematic that an FPGA represents.
That's right. You could actually write a schematic of what you ask the FPGA to do.
Whole gate logic?
You could, if you really wanted to.
If you really wanted to.
I mean, people do look
at
at memory.
I mean, that would be horrible. That would be, yeah. But somebody out there probably does do that.
Well, in school, the first time you program an FPGA, you do it with gate logic. You draw out all the gates and connect it together. And then once you learn VHDL or Verilog, you're like, why did they make us do that?
I'm never doing that again.
So
exactly.
Yeah. Right, yeah.
Okay. Let's see. We have actual questions here. Oh, right. There was this one. This one is a big baffling question for me. You like picks? Like, really? Like, you like picks? What did they do to
so
you?
that probably
that's probably just Steven.
Yeah, that probably. Okay, so I'll give just a short story on it. Picks are, I do like them, and one of the reasons why I like them, or a chunk of the reason why I like them, probably has to do with nostalgia. So at my school, I studied mainly semiconductor physics and analog electronics. I did very little digital electronics at my school, and that was by choice. It didn't interest me, and it wasn't big on my to-do list. But after I got out of school, I realized, well, I have to learn this sometime. And so just not knowing so much about it, I just decided to go with PIC. And I taught myself everything, microcontrollers based on PIC architecture, and I literally just got a data sheet and read the thing cover to cover, like 300 pages, just because I was like, I want to learn all of this stuff. And so I started with PICs, and so they weren't really that foreign to me, because of that. Now, I've seen other microcontrollers that are simple, but it's one of those things where once you learn PICs, it's kind of just like, well, everything that makes a PIC difficult compared to everyone else is sort of just like, well, you can just deal with it,
I guess I don't see the problem with PICs. I've used probably every single microcontroller family under the sun. I would put PICs very low on that list that I want to use again. But I don't see like an actual problem with them. They're especially the older ones, the data sheets are not very good sometimes.
Oh, and we had experience with that.
Yeah. Finding a footnote, figuring out why GPIO is not, flipping around. So,
but when it all comes down to it, I know I'm grossly like generalizing and making this too simple here. But what I've personally found is that, when you switch from one microcontroller to another, most of the time you're still programming in C. Most of the time, all of your stuff is generally the same. You just have to scour the datasheet to find, oh, hey, this configuration bit needs to be that, or I have to use these capacitors with my oscillator, or blah, blah, blah. Like, the rules generally stay the same between different families. It's just a matter of finding, like, whatever syntax differences you have to do to make it say hello,
Yeah.
So when it comes down to picks, it's just like they're the family that makes me do these things, whereas pick any other microcontroller, they're the family that makes me do those things.
I'm biased against picks because I don't like their programming interface and their fussiness with C.
You mean the MP Lab X or whatever? Yeah, it's a little bloated and confusing at first.
And they have some interesting things that you can do with interrupts and motors and whatnot, but they put a lot of burden on the programmer, where other processors have taken more of that into their hardware abstraction layers or written more code for you that shows you how to do some of the more complex things. But PIC kind of throws you and says, read our 300-page data sheet. I don't care.
Well, PIC really loves you to access individual bits within registers.
Yes,
and it loves to do bit masking and bit shifting. Like it to get into PIC, you need to know those things. And to be honest, I find that kind of fun. I actually like doing that. But I can understand that, like, the abstraction of, hey, this is like a pre-built-in motor driver within our PIC where all you do is write to a register and a motor does a thing. Like, I can understand why that would be appealing.
See, I'm a big fan of the parallax propeller, and it's like the exact opposite of a PIC.
Yeah, I was about to say.
It has no hardware peripherals or things like that, so you have to write everything. Which is kind of interesting because you're basically I need to have SPI, so I need to write software to emulate a hardware SPI.
Right, but it's fast enough and it has enough cores that you can just do it.
You turn one processor into a hardware SPI, basically. It's software still, but it's dedicated to do SPI.
Yeah, and since it has a whole bunch of little processors in there, you just allocate them wherever they need to be.
Right. So if you're not a fan of PICs, what are you a fan of?
Well, so
ARM standardized Cortex, and now you can get Cortex from a number of different vendors.
Pretty much everything's ARM.
Cortex M's. While I have used an MSP 430 pretty recently, and I have used a couple of stranger TI chips, I prefer the Cortexes because there's less to learn between vendors.
I was about to say it depends a lot on the project. For the kinds of things we've been working on, historically, they've been somewhat high volume, very feature-rich kind of things, sensors and Bluetooth and stuff like that, which kind of pushes you to a different level. And I know PICs have higher-end ones, but
Cortex M0 Pluses are pretty dumb and pretty small and pretty cheap.
Compared to a PIC?
Compared to an 8 or 16-bit processor, there are some out there that will compare well in the price range, yeah.
And in the power range?
Oh, yeah.
Oh, okay. Well, that's fine.
I don't know. I always thought it was funny that software engineers tend to prefer anything but PIC, and hardware engineers tend to prefer PICs.
Always. Every time an EE has designed something and it has a micro, it's, here's this, and here's a PIC 16 doing something.
I think it depends on how old the engineer is and what they learned. It goes what Steven was talking about. It's like he learned PICs, and so he's just like, I'll grab my bag of knowledge and plop it on the desk.
Well, okay, so I'll do a little bit of a defense right here, but this comes purely out of the fact that Parker can tell you without a shadow of a doubt, I'm not a software developer. I'm not a programmer at all. Like I can dig my way through something and make it work, but I'm nowhere near good at it. So Pix I like the fact that I know, hey, I write to this bit and I activated a thing. Like there's like a give and trade right there. Like I pay that register money and it gives me what I wanted from it, sort of situation. So it's like, I like that really low level access to what I want something to do. And to be honest, like what Parker was talking about with the propeller, writing his own SPI driver, I actually did that on my first pick also. I just, wrote my own function to do that. That was all just a port call function, basically, with some like while loop delays and things like that. And it worked fine. And so like I like having that, like I've always had trouble with like relying on other people's libraries or other people's like stacks of whatever they have going on, just because it's just like a level of, I guess I don't trust that, or I don't trust myself to implement it properly. So I can just write it myself at the lowest level, almost assembly, and just, it works. That comes from a non-programmer's mouth.
It's a very understandable methodology, but, and it's one I kind of share because I enjoy writing the code, and reading code even now is harder than writing code for the most part. I'd rather read the data sheet and then write the code than read somebody else's code. But as even the smaller chips get more and more complex, I feel like I have to use some of these hardware abstraction layers, or at least be able to read them and take out the pieces I want, because more clients want the whole project done in a week because they think that that's possible.
Well, and you're giving away part of your chip if you not to attack you for bit banging SPI. We've all done something like that on some device, but if there's a hardware block that does it, you should use it. You should really use it.
It'll be faster.
It'll
be
using
less
your CPU.
buggy.
Yeah.
And even though it will take longer for you to implement initially, it will have the features you need.
Well, and I don't know if it would take you longer necessarily.
Mentally, you always think it will.
Yeah.
I was just about to say, like, I have a funny story about it, because so yes, I've made both hardware and software SPI drivers and things. I spoke to an engineering manager of a large audio company, year and a half ago, and we were talking just about a couple of their products, and he actually confided in me that they don't use any hardware communication drivers whatsoever. They don't trust the bare metal to do that. They write every communication driver in their firmware, even if their chips have like a SPI hardware level on it, which is interesting.
Doesn't make any sense.
It doesn't. But they don't trust it. Their entire engineering team, and it's like 15 guys on this hardware team, and none of them, they will all write their own.
Bad news for
SPI
people
drivers.
who don't trust things like that. They should not get into cars, airplanes, boats, walk on the street, use computers.
You're giving away so much of your time
and money
and effort towards something that is totally pointless. Use the tools available. I mean, that's like saying, oh, I wanted to build a house, so I made a hammer.
Well, here's the other thing, is those hardware blocks that are doing the peripheral things are verified by hardware engineers, right? There's chip verification. It's very rigorous. Writing a bit-banging software driver, you're going to write bugs.
You write it once and you have bugs forever.
Yeah. There is an advantage of not using that kind of stuff. I'm still saying use hardware, but like not using other libraries.
Oh yeah, sure.
Like the difference between, like let's just take Arduino for an example. Like the Arduino analog read versus, if you look online, there's a library called Analog Read Fast, and it does it like 100 times faster. It basically just cuts out all the in between calls.
Even digital read and digital write on an Arduino are unbelievably slow.
I feel like bringing up Arduino isn't fair. This is like
It's a bunch of libraries stacked on top of an IDE that are just guaranteed to make every call slow.
Okay, so Arduino. I love Arduino. I really love Arduino because it helps artists and people new to development, and it helps kids get interested in hardware and software.
I mean, I'll admit, I use it time to time too. It's really good at prototyping. Like your first thing you ever talk to a new chip or whatever, I'll usually try to see if there's an Arduino library already, just so I can get it working out of the box, and then I port it over to whatever I'm using.
Right. But I do not agree with people who are using Arduino professionally. And I have so many reasons for that. But what you're saying is exactly true. It's not fast. It's not efficient. It's really expensive for what it does. It's just not the right choice. It's a great choice for prototyping and for getting into things and for just playing, for not worrying about, am I going to make 1,000 of these? Just goofing off, making the lights blink, the fun part. But once you're really serious about making something like professionally or commercially, that is not the right choice. So I'm not defending Arduino as a software development environment.
I guess if we're still on microcontrollers and stuff like that, like my current favorite right now is the EFM8 platform by Silicon Labs. They're just cheap, like 40 cents in singles.
And they're robust, and you can get fast versions or low energy versions, and there's a lot of stuff you can do with them.
This is an 8051.
Yep.
No,
what's wrong with that? There's nothing wrong with that.
There's like millions and millions.
They made
of,
great music
of
in the
support
70s.
Code lines for that.
And you know, it doesn't even matter. Like if it's an 8051 under the hood, you're compiling C to it. It's not like you're having to look at, well, I look at the object code sometimes for time critical stuff, but
which this is probably a great example of where hardware guys, look at it differently. Would just say, if it works, it works. Does it really matter what the processor architecture is and what that's going to be, in the end?
Oh, and if it works, no, it doesn't matter at all. But an 8051 is not going to be as power efficient or as processing efficient as later developed cores.
That's the thing, though, is I can't find. So I developed a product on it called the Macro Watch, which is a binary watch that runs on a coin cell, and in its sleep mode, it pulls only like 7 nanoamps.
I think you calculated something like it has 10 years of battery life. If you never turn it on.
Yeah, if you never turn it on, yeah.
But it will keep time for 10 years.
Assuming your battery doesn't self-destroy, but
yeah,
that's an entirely separate issue.
But yeah, it's like that's the Sleepy Bee line. They all have like something B as their names. I really like it. Their IDE can use a little bit more work, but it works well enough. It's definitely better than Arduino one.
I like their graphical representations of the chips and their pinouts and things like that. That's kind of nice.
And they're really, on the hardware end, it's really easy too, because they actually, if you don't need timing constraints or anything, you can just use the internal oscillator, and all you have to do is get a bypass cap, and it's pretty happy.
Internal oscillators are awesome.
Yeah. And this one's even got, like, if you have an external clock, they have like programmable loading caps. So you can set what the load caps are. So you don't even need external load caps.
And they have a pretty wide range too, right? Of like what caps you can choose. If I remember right, there was like a handful of caps you could choose.
Yeah, but not the one I needed.
Oh. Of course, right? Yeah.
So
it had to be that way.
So I actually had to when I was setting up the loading caps, because if you get it off, because this is for like an RTC, so you have to use a 32.768 kilohertz.
For timing purposes.
Yeah. I think that's the right number. But you had to load it right, because if you don't load up those crystals right, you actually will get drift and it won't oscillate correctly. And so I actually had to kept playing with what loading cap to use, and I got kind of close to where you'd get a 1 second pulse coming out of the chip.
Right. I'm still not convinced with the 8051, but
you just need to go to Jay's $1 microcontroller. He talks all about it.
The microcontroller, the $1 microcontroller, it does give that one a pretty high bar.
I mean, it's not like they just took an old 8051 and repackaged it.
I know.
They put new bells and whistles on it.
It's actually got really powerful peripherals. Like the hardware it has is pretty impressive.
And that's what they do. They make a core that's super small and power efficient, and then they can turn off all of the peripherals they don't need.
I think his biggest complaint was that when it's not in sleep mode and you've got the clock turned up, it's
a little hungry then. Efficient.
All right, cool. Let's see. Moving on, I have other questions for you. This one I liked a lot. If you could, like Matrix style, learn a software skill, something you don't already know how to do, what would you learn?
Web development.
Really?
Like making pretty web pages, or like making deep
applications,
databases?
So like like AWS kind of stuff. Like using React, JavaScript, and stuff like that.
Why?
That's what everything's built in now.
But it doesn't change the physical world, and that's the fun part.
I've been building things that change the physical world all my life. I've never built a web app.
Like a purely soft thing?
Yeah. I've never done it before, and that's what I've been kind of, learning on the side is learning React and that kind of stuff. Because it's stuff I've never, like the first time I ever hit an API endpoint and I got data back, I'm like, holy crap, that changed my life.
Yeah.
Like I waited 28 years to try that? Damn.
Well, I can tell you what I would do. In fact, we talked about this last Thursday at the Houston Hardware Happy Hour. We had a group of hardware engineers all hanging out at a coffee shop around here. And I mentioned one of the things that I truly have no clue. Like it's magic to me. I would love to be able to write drivers for Windows. Like, what does that entail? What does that take? I don't know. Like, how do I make bits flip on my device and Windows detects it in a way that is intelligent? That's magic to me.
How do you want to plug it into your Windows box? Like USB?
Sure, USB. That sounds fantastic. Let's
parallel port.
Yeah, parallel IDE. Yeah.
I mean, with USB, you have to get a microcontroller that can speak USB, and then usually those can pretend to be keyboards, or they can pretend to be mice.
But he wants to write a real device driver. It's part of Windows.
I don't want to. Yeah, I don't want to pretend.
To go through the
I want it
Windows
to be like the real
stack.
thing.
He wants to make the Craigulus Special 3.
That's right. Yeah.
And so he would have to have a Craigulus driver.
Basically. Well, it's not that I want to write it. I just want to understand it. To me, Windows feels like it has 8,000 layers before you actually get down to a bit turning on a transistor somewhere. I know the bit turning side, and I can move my mouse, but all the layers that are in between are just a mystery to me.
Well, where Linux has a very separated kernel and application space, Windows didn't have that for a long time. They didn't do as well at making it so that you have an administrator who can install drivers and a user who can use drivers. And because it took them so long, they kept having little layers that would protect/allow until you have this monstrosity. And they kind of cleaned that up in Windows 10, Windows 9, Windows 8, whenever they went
there was no 9, 7.
So, okay, then it must have been 10. But it's still, I mean, if you wrote a Windows driver before, you can still see all the layers. That is an admirable goal for understanding and very pointless.
But if you want to do that, I would actually start with Linux.
Yeah.
Because
would start
the
with Linux.
concepts aren't going to be totally foreign, and you can see everything.
And then you start looking at Linux and POSIX and what it means to write a driver like that. And then if you wanted to go over to Windows would make a lot more sense because it would have some of the same terminology and some of the same layers.
Well, okay, here let's go on this topic real quick. You said it's pointless to do that. Well, no, and I love that. I think that's fantastic. But explain to me why, from your perspective, because you have way more of knowledge about this. Why is that pointless? And I'm asking that, is that because there's 1,000 people who have written things that I could just implement and it would just automatically work, or why?
Windows doesn't want you to, because Windows has worked really hard to keep hardware more under control. And so they provide a wide variety of USB drivers, because that's how most people plug in these days. And with the USB drivers, those are already in the layers. They already are well understood, and you can open up things. Now, if you go out and you get a Maxim USB chip or a STM USB chip, you're still going to have to fuss with the USB to make it so that it works. But the bytes will come in one after another. You won't be playing with the single pins that you want to play with, because Windows doesn't want that. USB is already a standard.
That's the fun part.
Yeah,
I like that.
You can make a PCI device.
You can.
Then you can't?
You can.
Oh.
But then why would you not use one of the billion PCI descriptors already out there? And it's kind of like for USB. If you could, you absolutely should use one of the. And then if you're using a USB thing and you want to have your own driver for it, you're still writing on top of the USB stack. It's not as deep a driver as touching bits.
Okay.
So, Stephen, you need to design your own OS now.
Yeah, I think that's what I'm getting at. In order to touch bits, I need Kraig OS going on here.
Well, if you really want to look at it, the Windows DDK is the thing you're after. Driver development kit.
I went to.
So I have sniffed a driver development kit before. At a previous job, we were doing something that required it, and one of the other engineers was there, and he was kind of walking me through what he was having to go through in order to do it. And I say sniff because it smelled pretty bad. It wasn't something that I wanted to even touch, because it was just like, oh, this looks horrible.
But that's what you want to do.
Well,
that's why he wants to have it just
theory,
given to him.
I want to do it.
Yeah.
I guess it just purely comes out of a just not having a good understanding of it. Like, I'll give this as an example. I have a piece of test equipment back at home that is a voltage standard. So basically, you flip switches on this thing, and it outputs a voltage, and it's a really accurate voltage standard. Now, it has an entire GPIO bus on the back of that, which using whatever protocols they have defined in their data sheet, I could control this thing via however many ways I want to. Now, I like that because the data sheet just kind of tells me you do this and it does that kind of thing. And I love that, just like down to earth GPIO. I have a connector here. I throw some bits at it and I get something out of it. Now, the connection from there to some kind of higher level thing, such as Windows, that's where I'm like, I want to learn that aspect. And it's purely, I guess it's mainly educational for me, more than I don't need to actually do it, because I know that there's 1,000 ways that someone else has done it, guaranteed way better than I could.
I actually think Chris's suggestion of try it in Linux first is a good one. I mean, this is an instance where a Raspberry Pi would give you hardware access and let you build up whatever you wanted. And then once you had that plan and could see the layers on the Linux side, it might make a lot more sense on the Windows side.
Yeah, actually, you can probably just glue a Raspberry Pi to the back of this thing and do direct GPIO access on your Raspberry Pi and
And serial port to the other side. Just type
You see
that
that part is fairly simple.
Yeah,
and
that's no fun.
I've already done that on Raspberry Pis. I'm not saying like that's boring or anything like that. I love the fact that the Raspberry Pi, you have a full computer that has an OS running on it, but if you want to talk to a pin, you can straight up do that.
I got it.
Yeah, that's not fun at all.
Put a Wi-Fi on the Raspberry Pi, so now your voltage standard is an IoT device, and you can just SSH into it over your network.
That would be fun.
And then run whatever you want.
That would be a lot of fun.
But yeah, that's why there are so many Raspberry Pis on the net.
Well,
Remember
okay, add it to the project list.
Yeah. Okay, what hardware skills should I learn as a software engineer who wants my doubly to appreciate me more?
Let's see.
So I actually have one that I think would be fantastic, and we have something. Well, I believe you guys actually have something written out about this, which is funny because I think both sides kind of argue about this same topic. It's the idea of reading and interpreting schematics, because both of us have to play by the rules of the schematic in a way. And one thing that would be fantastic is for software people to be able to look at a schematic and get a lot of the answers that they need to. Not necessarily exactly how everything works or all the equations that go behind it, but things as simple as, hey, this is my input signal. It's going to this pin, and I can see that because it's this part of the schematic, or something of that sort. So just a general ability to read a schematic is a very valuable skill, in my opinion, for a software developer.
How did you learn to read a schematic? Did you learn to read it by writing it, or did you ever learn to just read it by reading it?
So I'm kind of weird, I guess, but so I kind of taught myself how to read schematics back in high school because I wanted to build guitar amps, and I started downloading as many schematics because I knew that was the way that they were built, but I didn't understand them. So I just spent a ton of time looking at a bunch of them and reading a bunch of information until eventually I could identify all the individual components, and it just grows from there.
I got mine reading appliance wiring diagrams. So it's not quite a schematic, but it's kind of close. Repairing appliances and stuff when I was in high school. So,
okay, so you both did learn to read them before you learned to write them.
Oh, for sure.
Oh, yeah.
Okay. I learned to read them, but I always wondered if it would have been easier if I had been writing them first. Because now as I can sketch them, I can read them better. But it took me a long time to realize that there was a lot of the schematic I didn't need to follow. That there were whole pages I could kind of just mark off as, this is power conditioning. I don't care. Just give me my 3.3 volts and go on to the next page.
Yep. That's actually a good point, is like maybe if you're working on a team, part of your schematic is this is what matters for firmware and this is what matters for software.
Absolutely. And notes on the schematic are invaluable.
Oh, yeah.
So fill it up with notes as long as it's not super cluttered and you can still read it.
I would say reading schematics is probably the best way to improve your schematics that you're writing, because you learn why isn't this explained, and then you put it on yours.
Right, and be logical about your schematics. I mean, chunk things into circuits that make sense to be together. It does help to have a path through which signals flow. If you're a right to left guy or a left to right guy, it doesn't matter. Just pick one and stick to it.
Stick to it, yeah.
Yeah, and have it such that, if you have, like you were saying, if you have 6 pages of signal conditioning that connect a thermocouple to a processor, let your firmware guys know that, hey, pages 1 through 6 you don't care about. Page 6 or 7 is the one where your signal gets into the microcontroller or something like that.
Well, and you also should specify what kind of signal that is. So, like, if it's an analog signal, it'd be like, it's going to be in this range.
Right. And you can expect these values in your code or something like that.
Well, that's a point I'd like to make, because you say you can ignore parts. But what you're talking about, signal conditioning, sometimes we can't ignore that because there have been certainly instances where that hasn't been done quite right.
Oh, yeah.
And it bites us in the end because we have to end up fixing it in firmware with like, oh, we have to do this. We have to reinterpolate this entire range because it's nonlinear when we expected it to be linear, or we have to correct it for some other thing. But there's a lot of cases like that where if somehow we'd been involved in the analog design, which we can't understand, you see where I'm saying? You know what I'm saying?
Oh,
Yep.
yes.
Well, but the way you're describing it, what that sounds like is, not necessarily, I'm not saying like this is the end of the world or a horrible issue or anything like that, but it sounds like the hardware guys, maybe they either were relying on the fact that they were hoping that their prototypes would just work, or maybe their calculations weren't right, or maybe they were expecting that we were going to do this in the future where we might have to, apply a polynomial to whatever, and I think that goes back to what I said a bit earlier about you got just got to have communication between the teams. If somebody makes a decision such as, hey, I'm not sure if this signal conditioning part is going to work, we're just going to have to try. Well, that's an acceptable, solution.
Absolutely.
Just make sure everyone knows that.
Yeah.
Mm-hmm.
And it's nice with the analog bits that I'm not following to be able to say, well, can you walk me through this? Especially if there's an answer at the end that says expect voltages from 1 to 3 volts.
This goes into software.
And then I'm like, okay, 1 to 3 volts. I can totally get that. What does that represent in physical units for the sensor? And then that's really awesome. When you do schematics, do you have lots of lines connecting things, or is everything net named and then you have to search for the net names?
So for Steven and I,
we're different at
we
this.
do it completely differently. I will, if it's ground or the power in its logic block, so to speak, they are all connected and they will have a symbol, whatever. If it's a signal, if it's a signal that leaves the logic block, it gets net named. If it's inside the logic block, I usually will name the nets unless there's no reason to name that net for some reason. Those all get connected. But so if you have like your power filtering over on one side and then your microcontroller on the other side, I don't go and connect like the power good signal.
So usually the things that I make into like net nodes are power, sometimes ground, but a lot of times I'll draw out ground because a lot of the circuits I work on are very strict on how ground has to work. So power is almost always just a net name because it's just power. Now, I block things as much as possible on my schematics. So I'll put my whole microcontroller, and if I know it has, off-board RAM that's next to it, I'll put that right next to it on the schematic, and I will literally draw boxes around the things, and I will name those boxes. I will say, this is the USB input IC. This is the microcontroller. This is the memory. I will put notes all over the place on things because it just helps things stick in my mind. Now, if it comes down to things like SPI, and I've got like 50 chips that are all on the SPI bus, I won't draw 50 lines everywhere. I'll just say, hey, this is, the couple lines for SPI. I'll make those buses, and you can look at every chip and see, hey, this is an SPI chip because it accesses those buses. I've found that that's the easiest to read. And in general, my analog stuff is all physically wired. I mean, not physically. You see the wires on my schematic, and my digital stuff is all blocks that are all named.
This seems like a trend that has changed over my career. It used to be everything was wired together, and you'd end up with these schematics that were mazes, and I would feel like I was doing those third grade games where you have to follow the line. And I remember getting out markers and trying to figure out where everything went because some of them didn't have names. And I remember in an interview, somebody handed me a schematic that didn't have very many names and asked me what chip did what. And I was shocked to discover that I could tell which one was the flash chip and which one was a sensor just because I had enough experience looking at these things by then. But now it seems like nothing is connected and I have to do this game of trying to this is the other third grade game where you have a list over here and a list over here, and then you try to draw the lines in between to figure out what connects. And I don't like either way.
There's a balance for sure between the two. Like if you're just naming every single pin that comes off of a microcontroller its own individual name, and then you have to hunt and peck for every single one, it's annoying. It really is.
That was how I used to do it.
I've seen some of Parker's old schematics, and it's just like, so you just know it, but it's really hard to read.
Even before that, because I learned by reading wiring diagrams, is I drew them like wiring diagrams first.
Oh, geez.
So everything was wired.
Yeah. Actually, if you want to have fun, go to Google and go look up the original schematics for the Apollo guidance computer. If you want to see schematics where every single thing is connected to every single thing, it's like, I don't know how many pages for that original computer, but it's like gate level logic. No, it's more than that. It's far more than that. Far more than that. And it's all gate level logic, and they're all just connected to each other. And they just have like page in and page out connectors named, a ton of random things.
And they used to have the schematics be, 4 by 4. I remember printing them out on the big plotter at work. And it wasn't like 8.5 by 11s.
Oh, 4 foot by 4 foot.
Yeah. They were enormous, and they would go on the wall.
Yeah.
I was thinking, you said 8 by 11 after 4 by 4. I'm like, 4 inches by 4 inches?
Yeah, you might get like 2 or 3 gates.
I'm like, what are we talking about? Coasters?
Yeah, coasters. Yeah. Well, they used to have a whole army of people on drafting tables writing all those up.
Yep.
Yeah, that must have been a lot of fun. So from okay, let's crack into the software side of things. In terms of schematics, what would you prefer that we do that makes your lives easier?
Definitely the thing you were talking about with putting blocks in common places and marking them. Having the schematic be part block diagram and part interconnection, I think is super helpful. Because we don't really get block diagrams anymore.
Yeah, block diagrams are really cool. Although I noticed in Altium, they're doing more with the block diagrams. A couple times now, I've seen the hardware guys use net names on the block diagrams that are then reused in different places inside. So
that's not good.
Power, they'll use power in different places, and it means 3.3 on this side, and it means 5 on that side, and I'm just like, shoot me now. And then the person who told me this then said, "Oh, it's object oriented," and I swear I almost shot him. But I'm much too nice for that.
Wow,
I was pretty violent. Sorry.
That's awesome. Yeah. Okay.
Yeah.
Well, we'll make sure we always have all of our power lines, defined properly.
So, what's the proper way to do that? Is it 3.3, 3v3?
Oh, I don't care. As long as it's consistent.
Hang on.
This is actually a question for Steven, I guess.
Well, but the thing is, when you start getting into it, sometimes you'll have a 3.3 digital and you'll have a 3.3 analog, and those are different power supplies that you want to be different, and they go to different things.
And so one should have an A at the end.
I usually do DIG and ANA at the end, just to make sure that it's
crystal
know
clear.
what it's going to. Yeah. So that's really what it all boils down to. As clear as you can be. If it takes you an extra 2 seconds, to just always ask yourself, if someone else was reading this, would they be able to get it? Mm-hmm. I think that's kind of one of the big things there. And everyone has their own way of doing it. You hand 10 projects to 10 hardware engineers, you're going to get 10 different schematics, and they're all going to have the fingerprint of whatever engineer did it. But they should all be readable at the end of the day.
It's funny. In software, we have coding standards, and part of the reasons to do that is so that our code looks less individual. Is there ever been a hardware schematic standard? I guess there probably is.
I mean, technically, everything on a schematic is, a standard. Like when you look at a transistor, it should look the same across everyone's computers. However, Parker, did they ever teach you how to draw a schematic in college?
No.
I never once opened a PCB program because of college. I did it on my own, and so anything we did was just like whatever wires we had to do in our lab notes to get by.
I mean, I can think of 3 different ways to draw a resistor.
Yeah,
on a schematic.
Right, there's a bunch of ways. And it's different actually based off of, where you are in the world. In the UK, they draw resistors as a box as opposed to a squiggly line. And so, there are some standards.
Angled squiggly line.
Oh, I apologize.
Because the squiggly line is inductor.
You're right.
That's
You're
a
right.
springy line.
It's
springy line, yeah.
That's right, yeah. So, yes, there are standards, and we like to pretend like we follow those.
I think he was talking about like the implementation of the hardware is going to be like, we can talk about like if you give us a project, like I'll use an EFM8 and then Steven will be like, I'm going to use a PIC for some reason.
Well, I mean, I do mean that, but also at the same time, like I was using a transistor, so let's run with that. Like an NPN bipolar transistor, the emitter has the arrow pointing out
of it.
It should always point out, regardless of how big or small or weird you draw it. It should always point out, such that that's the emitter. It might not be a circle. It might be a square. It might be whatever. I don't care. Whatever. As long as like eventually I can read it. I think that's where the standard comes in.
I really want someone to draw a really weird looking NPN transistor schematic symbol now.
Yeah, we should do that and then make a shirt out of it. And then write Macrofab Engineering Podcast under it.
I actually didn't mean a standard for the components because I guess I knew that happened. And I view
Although
those...
it sounds like less than I thought.
Well, yeah, a little bit less than I thought. I kind of viewed those in the same class as software keywords. It's like, no, you don't get any choice about those. You have to use those. I wondered if there was some standardization attempts towards net names and wire patterns and how you
I'm sure individual companies
put
have
together.
Individual companies will usually have like a document like for that, but no.
Yeah, I mean, it's the same as for code.
Yeah.
There's no.
Yeah.
Well, there are attempts to get us to start doing coding standards and
people publish them.
And people publish them, and
mostly,
some of our tools help us follow them.
Yeah.
Local variables are all lowercase. Global variables are all uppercase. Blah, 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 blah.
That sort of thing.
Yeah.
There's more and more standards, like actual legit standards for this stuff when you're talking about like defining footprints and packages.
Yeah.
But even then, people don't care. That's the thing about it's like people just don't care about those standards. As much as we talk about them,
I would think I would make the argument that that maybe they're not fully educated on them. And what I mean by that is like a lot of people don't know that those standards exist. Like when you're just doing an 0805 surface mount resistor, like do people know what IPC number document to go to that tells them how to do that? I would venture to guess 9 times out of 10 they don't know what number that is,
Don't you just get it from
It starts with a 7. No, DigiKey does not provide the layouts, and in fact, most companies will not provide those things because then there's some form of liability. If your circuit doesn't work or if it doesn't reflow properly or something, they'll give you guidelines, but they will not tell you exactly how to do it most of the time. They'll give you pretty good guidelines.
Are there... I heard something about a standard library of parts from a few vendors.
Yeah, I think DigiKey just started doing that with Kicad. This is getting to that kind of mentality with, I guess, hardware engineers, because where Steven was talking about like wanting to learn how drivers worked and like wanted to do it just to learn how to do it. And so it's his. That's how I think a lot of hardware engineers are with packages and hardware, is we don't trust like what other engineers do.
Oh no.
Like if Steven gave me a footprint, I probably would not use it.
It's other way around is probably true too.
Exactly.
And
Why?
it's not
Why?
Tell me where people hurt you.
When we first started with electronics, and the first time you spin a board and it won't work because you put a SOIC wide package instead of a
But you did that to yourself.
No,
Oh,
you
I see.
downloaded the footprint.
I
and
see.
You got somebody else's library.
Yep.
You just trusted that they did it right. It looked good, but it didn't work.
And the difference is when we hit compile, it takes 3 weeks instead of 30 seconds.
And
3
every
weeks
time
in
we
real
hit
money.
compile, it's a lot of money.
Yeah.
Right. So the only way to, the thing is you own all of your mistakes if you make a mistake, but you also own all of your successes when you make it. And I'm not saying like that's like virtuous in any kind of way, but it is one of those things where like the way you're right is you just do it.
Yeah. I would say, because if you did the design yourself and designed everything and you got it wrong, you can just hate yourself. You can't hate some random guy on the internet.
Sure you can. There are whole forums devoted to that.
Thought that was the point of the internet.
So, I mean, entering these footprints is pain, and it's tedious and boring and tweaky.
That's the most fun part.
I actually enjoy it too.
That's my favorite part of the job, is actually finding a new part and being like, I get to draw this out and CAD it out, and that's like the best part, is finding those new parts that got weird packages.
Yep. And a lot of the standards for these IPC standards I was talking about, a lot of times they don't tell you, hey, if you have a part that looks like this, then do exactly this. What they tell you is, hey, for this much pad coverage worth of solder, then you need to follow a 50% rule of blah, 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 things like that. So half the time they're not telling you exactly what to do. They're just like, you calculate based off of statistics that we know that this is going to work 99% of the time.
And so you end up re-implementing these fairly complicated things over and over again. Or
not for every board. I mean, Parker has his own library of like resistors that he always uses. I have mine. And like those, they're trusted because I've built boards in the past with them. And so I know that that's always going to work for me.
And I actually let's say it's like an 0805 resistor. Like the one that the package I designed is actually in between what a purely machine place footprint would be and what a like hand soldered footprint would be. And it has some trade-offs on both of those. So you can rework it by hand with an iron, or it will reliably go through the reflow oven, but you give up like board space for that.
So let me tell you what this sounds like to me. And I see where you're coming from. I really do, because this is mechanical stuff and there's physical things happening here. But from my perspective, this is like saying, well, every time I do a project, I rewrite the operating system from scratch. And I have some bits that I've written in the past, but I always use my operating system that I wrote, even if I'm making something, an iPhone app. From a software perspective, it's like, okay, well, I have everything I do, I've made myself.
That's not completely true. I mean, like, I will reuse all my footprints. It's not like
they're yours, right?
Sure.
Yeah. No, I'm not trying to argue. I find it fascinating.
it's a very different mindset from, especially, I'm going to a talk tonight about a library that in Python, and I don't think I really want to use this library, but I want to know about it. And
it's kind of like what you were saying about wanting to learn web development. That's completely the other end of the spectrum, right? Where you're only piecing things together from other people's things.
Yeah, you're not doing web development from scratch.
Is actually, I'm not. I do agree. I'm not doing it from scratch, but like because I'm writing a lot of it in Python and JavaScript, it's like if I hit import and insert Python thing, that you can import, which is like everything. I actually will go to where that stuff resides and read it and like, how does that thing work? Because I just want to import something and it does something else,
Okay.
I read the API about it, and I'll read a function or two if I'm unclear on the API, but I trust the APIs and then go on. And it's only when things go horribly wrong that
But like they say, when things go horribly wrong for them.
For them, it's money and time. And when it goes horribly wrong
and
for
let me
me,
also
it's
give you a
just
little bit
time.
of a story. At a previous job, when we would do a new product, if it was just a prototype, usually there would be a handful, up to like maybe 3 engineers who worked on it, and they would kind of go off into a hole and do their own thing. But when we were getting closer to going to production, we would have a full design review where, up to, 3 to 5 engineers would go into a room for days on end. And what we would do is we would go every single item on the schematics. We would pull up the data sheet for that. We would pull up the footprint for that. We would measure everything. We would double check everything because, every footprint was created. And to the company, that was actually more valuable to pay multiple engineers their full salary to do that than it was to order, 20 boards and all of them be bad because one footprint was off or because, one thing was off. The cost offset was good enough for that.
So you each write your own individual operating system based on things you've done before, and yet you believe in
usually
code
your
reviews.
company has like a set of footprints.
That's right. Yeah. This company that I was talking about here, they had been designing circuit boards for 25 years. So they had success placing a resistor, over and over and over and over. So we would use that resistor package. It was trusted, it was known, it was good, and it was to IPC standards. But if we made a whole brand new funky sensor, there might not even be a package for that. You had to create your own package, or some kind of weird chip that we didn't have in our library. You have to create it for that, So I think it's unavoidable in a lot of ways.
You have code reviews. You have detailed, in-depth code reviews of actual important information and not just fluffy names and stuff. It's odd because you have, as software engineers, we trust our libraries a lot more than you do, but we don't always get to have really good code reviews because we trust our libraries, and we're throwing Lego blocks together, and if they stick, then yay. And if you get to have code reviews to say, oh, those two should be moved over, that's awesome. But a lot of times when you're working in a small team, you can't even do code reviews.
I mean, isn't that what happened with the SSH bug that was, a couple years back?
The go-to bug?
Is that the right one? I think it was the heart
Did someone use a go-to statement?
No, there was. I think it was the heart thing.
Heartbleed.
Yeah. Was that the SSH bug?
That sounds right.
Yeah, it's interesting. That was such a big thing at the time, and now it's like,
no, Heartbleed was
anymore.
SSL. It was in TLS.
That's it. Yeah. Yep. But it's like that was something that's been there forever, and it finally took someone to look at it and be like, oh, that's not good.
To look at it, to understand, and to report. There were 3 points there.
Yeah. But it's that same thing where, like, at least someone could just press compile on that one again. Well, and then update all the systems.
Yeah, that's a tricky bit.
Everyone who uses it.
Yeah.
Including the embedded systems that aren't updatable.
Yes.
Well, and not to beat a dead horse, well, I guess we can leave this as kind of the last thing. Let's say that you used a footprint on a board that worked. It got through manufacturing. Everything is great. And then 10 million units got out into the field. And you find out that because of your footprint, that something could make it fail in the first 2 months of running. Then you're really screwed, Then you would have said, oh, I wish I would have looked at my footprint and made sure that everything was right about it.
But if you'd used a standardized footprint, all right. So
I guess that's the question. Why aren't there
standardized footprints
that everyone agrees and is tested? And
why is there not one standardized software code?
Well, we have only a limited number of operating systems to choose from.
We do. We have the languages, and we can't deviate from them while using them.
Well, you can use Python. Well, all I'm getting at is, like, you can use Python, you can use C++, you can use C#, you can use Rust, you can use...
But it sounds more like you're saying you can mix and match them all together in one.
No, why isn't there a standard language? One language to use all of them. It's the same thing in the hardware world where some footprints are better at other things than other ones.
Well, and I think so a little bit further than that, if you go look at the standards for even the most basic component, a resistor, even the IPC standards will give you 3 separate footprints that you can pick from, and they relate to 3 different manufacturing capabilities. If you want to do XYZ manufacturing in China, then pick this one. If you want it to go into space and be super reliable, then pick this one, and it's going to cost more and things like that. So the thing is, like, it's never just default. It's never just like pick one and you're good. I mean, for the majority it is, but it's not always going to be that case.
Wow, I'm sorry. That sounds really hard.
I wasn't trying to be mean about it.
No, it sounds really hard.
That was a really good explanation.
Yeah. No, that's.
So I wish it was that way.
Yeah.
And okay, so I'll admit, in some cases that is true. Like the software package that I typically use for laying out boards is called DipTrace, and I have found just through experience that a lot of their basic level component footprints are acceptable, like the SOIC style packages and things. The ones that are generally pretty easy to work with, they're good. And I will just use those. But I was really skeptical the first time I used it because I was like, I really don't know if it's going to work. And the good thing is you can open up their default libraries and check all the dimensions. So I did check all the dimensions and it was fine. But, in a lot of cases, I will just rewrite that stuff.
And also using somebody else's like footprint, that footprint never looks like your footprints. And so like you'll have this, and the text will be different, and it's like, ugh.
And they'll color it.
It's got to be my style,
like monsters.
Yeah. It's like if you opened up somebody else's code library and they got a completely different style. They use tabs instead of double space.
Those monsters.
I'm actually a tab guy, so.
Okay, so I actually have a quick question for you. I actually thought up with this question earlier. This is a little bit of a deviation, but still in the same world. So when it comes to a product, let's say that all 4 of us had designed a product together. Parker and I did hardware, and you guys did software and firmware. Let's say that we're going to need some kind of a change to that product. In your mind, should that start in the hardware team? Should that start in the firmware team? Who can initiate a change?
The sales team.
There should be a product team.
Never give the sales team an opportunity to change something because they will.
Usually, historically, there's a product team with the things I've worked on where people are defining what the product is, what features it has. It depends on what the source of the change is, right? So if it's a bug, is it something where we're going to have to rev the board? Is it something where we can do a firmware change? Is it a combination?
And it depends. It also depends where it comes from. Is it that there is no longer flash of this size, or the lead time is 28 weeks? So that definitely comes from hardware. Features for the user usually come from the software direction because that's
what they see,
who the product manager is complaining to. Because they think everything is software. There are system things. And a lot of the companies I've been to, you end up with either one hardware engineer or one software engineer, or a pair who really enjoy working together, acting as systems engineers if they don't have a separate role for that, who talk about, you want to change the flash. Could you also make it better? Or could you also make it bigger? Or you want to change the flash. I only use a quarter of it. You can make it smaller if that's cheaper. And if you have those communication lines, it's easy. But it does come to a big screeching halt when you're in production and the hardware engineer changes the flash, which has a different interface, and now you're in production and suddenly manufacturing has to stop because software no longer works. And everybody in the company is screaming at the software team.
Don't get me started.
And
you triggered them pretty hard there.
And how is that the software engineer's fault? There's a reason they get really angry at that point. But that's a failure of a systems engineer, or it's a failure of a management role, or it's a failure of the two leads who needed to have talked. It's a team failure.
That was actually another question I was going to ask. So let's just run with that real quick. If a hardware guy says, "Hey, I can shave 5 cents off by going to a different memory chip," how should he alert the rest of the team to say, "Hey, I want to do this. It's going to save us money"?
The nicest thing that a hardware engineer can do is to sit down and figure out the differences of the datasheet themselves, which they have to do. And then tell me about the differences. Ask me how long it will take. Like, just in general terms, is this a week-long project or a 6-month-long project? It doesn't, and definitely don't ask for like specific number of hours. You're just looking for a scale. Now, you take that scale and you multiply by your salary. You don't have to ask my salary. Just multiply it out by how many hours that is and how long it would take, and figure out if that 5 cents is actually going to save you money. Because engineers are quite expensive. And if you are only making 1,000 of something and you're saving 5 cents on it, and you're using 100 engineer hours, not going to compute. So once you have how long is it going to take, then you go back to your manager and you say, okay, they say it's going to take about this long. It will save us this much money in the next 6 months. Your manager goes talk to their manager. Their manager says, oh my God, you talked to the hardware engineer? Why did you do that? Or no, what they
You're
should
not supposed
say.
to talk to those people.
Yeah. They're cave trolls.
And now you have a value proposition. You're not changing things for a small thing. You're changing things to make the whole system, the whole team, the company better. And it doesn't feel like it's just, oh, I'm changing things because, I don't know, some vendor took me out to lunch, which I swear I have felt that way, that like the only reason this changed was because someone got a good lunch out of this.
I mean, I would do that. I'd change a part if I got a good lunch.
Well, because you're just changing the footprint and I have to do all the work. Should have taken me out to lunch at least too. Yeah. So
That's a good point.
I really like the idea of making sure you come at it from a team and systems perspective, even though that makes it a little bit harder. But as you said earlier, if you spend an extra 20 seconds or an extra 20 minutes making someone else's life an hour or two easier, then you've won. It's a team sport these days. I know we're all individuals, but it's still sadly
Except for footprints.
a team sport unless you're making your own footprint.
Except for footprints.
If we were all here, we could have a big group hug now.
Yes. That's actually a really good point to leave it on. Unless you all would like to have final thoughts, closing arguments.
Closing arguments.
One more.
Okay.
Debouncing a button, firmware or hardware?
Oh, Parker's asked me this one before.
Hardware, because I'm lazy.
It depends on the quantity. If it's more than 10,000, then I'll do it in firmware. But if it's less than 10,000, buy your own capacitor.
I think the last time I answered this, I said both.
Yeah,
Wow.
I usually implement
Belt
both.
and suspenders.
Yep. Well, if you talk about like FCC CE testing and stuff, it makes
Right.
a lot of sense to do it that way.
Yeah, I mean, it's wise in software to always debounce your buttons, or to admit that you don't really care if you hate your user and have them push the button twice.
Yeah. You know, okay, and here's a quick gripe that is totally off topic, way big tangent. Something that I think really needs to change, and I don't know if this is a hardware or a firmware thing, but when you're at the gas pump, any gas pump, it doesn't matter, pick any single one. Why are the computers so damn slow? Like,
Okay, so
if I press a button, it should just go.
You should hear Christopher's rant about point of sale systems and how awful they are.
I think they're slow on purpose.
I'll answer it this way. Lowest bidder.
Yes.
Oh yeah, okay,
Yeah.
that makes sense. Yeah, just make them a little bit faster. Like, it's the only thing about making it slower. The only thing it hurts is the guy who wants to go fast. Like, everyone else can go slow if you want to.
They could sell more gas if they could put people through faster. Yeah.
Yeah.
They're losing money.
There we go.
You see the new gas stations, right? They have screens that have like ads and stuff on them.
Yes. Yeah, and they yell at you. That's where all the computing power is going. Video decoding.
Yeah.
That
It's not going to the buttons. That's
ads,
for sure.
The ads buffer quickly. It's actually like when you have to type in your zip code, that takes forever.
Oh my God. It's horrible. And then you
really
accidentally hit
debound.
cancel and it's game over if you do that. Like,
Usually when that happens, just change pumps.
yeah, no, I've done that. I've literally driven to another pump. Yeah. That's my closing argument there.
All right. Yes. Well, this has been a crossover show of the Macrofab podcast with Stephen Kraig and Parker Dillmann, and the Embedded FM podcast with me, Alicia White, and my co-host, Christopher White. You can find both podcasts in your normal podcast app or look on their websites, macrofab.com under blog or embedded.fm under
Embedded.fm.
Embedded.fm. Thank you to Christopher for editing, as well as being my co-host and producer. Thank you to Stephen Kraig and Parker Dillmann for joining us. And of course, thank you for listening. I have a final thought to leave you with, because this is something we do on the Embedded Show. And my final thought this week is from the painter Bob Ross. If we all painted the same way, what a boring world it would be.
If we all drew footprints in the same way, what a boring world this would be.
Embedded is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive money from them. At this time, our sponsors are Logical Elegance and listeners like you.